In this video, we will see an example of a relative velocity in which we will see how two different observers observe the same object when they are in different frames of reference. So here we are having a situation where a ball is kept on the seat of a car and it is at rest. So we are taking two observers, one inside the car and one outside the car. So the observer who is outside the car is at rest, and the observer who is inside the car is having the same motion as that of the car. So right now the car is at rest, so the ball is also at rest, and both of them have the same observation, that is, ball is at rest. Now let's say the same car takes a turn. So now the ball will move towards right. This is our practical observation. So if the car is taking a turn towards the left, the ball inside the car will move towards the right. So what does the passenger who is sitting inside the car observes? The ball is moving. That means there has to be some force acting on it, and he calls this force as fictitious force. Now we are assuming here that the passenger who is inside the car cannot feel the motion. That means he does not realize he is in such a situation, such an idealistic situation, that he cannot feel the motion of the car. So what he would think, the ball is moving without applying any force. So Newton's second law says that there has to be a force. So he assumes that there is some fictitious force which is acting on the ball towards the right, which makes it move. What about the person who is standing outside? He sees the ball is moving due to inertia. Now, how do we explain inertia in this case? The ball and the car, before taking the turn, were moving towards right. Correct? So, as soon as the car takes a turn, that means the car is changing its direction, but the ball, which was moving initially towards the right, would try to keep its direction because of inertia. That means the ball will keep moving in the right direction because of inertia. That's what the second observer gives the reason for the motion of the ball. So ball is moving due to inertia. So again, your concept of inertia must be clear here. Inertia means to retain whatever state of motion you are in. So the ball was moving towards the right, just like the car, because car also was moving towards the right before taking the turn. But once it takes the turn, the ball keeps moving towards the right, and that's why that explains its rightward motion. So we can see two different observations by two different observers. One observer is outside the car and he is at rest. Such a frame of reference is called as inertial frame. But the passenger who is sitting inside is moving just like the car, just like the ball. So he is in non-inertial frame. Okay, in this video we will see how to solve the problem based on inertial and non-inertial frames of reference. We have a car in which there is a ball which is attached to the roof of the car with the help of a string. The car is moving towards right with an acceleration a. We have got two observers, one is standing outside, one is standing inside. The one who is standing outside is inertial observer, whereas the one who is standing inside is non-inertial observer, because we know that non-inertial frame of reference is the accelerating frame of reference. Now for inertial frame of reference, the inertial observer has to give a reason why would the object accelerate. Okay, and for non-inertial frame of reference, the object is in equilibrium in both vertical and horizontal direction. So we draw the free body diagram. Now for inertial observer, we can see that it is in equilibrium in the vertical direction, so t cos theta is equal to mg, whereas in the horizontal direction, you've got t sine theta, which is equal to ma. Quite straightforward. But for non-inertial observer, we have got it is in equilibrium in vertical as well as in horizontal direction. So we will see that mg is equal to t cos theta for vertical. But and in horizontal, how does it differ from inertial frame? In horizontal, you've got t sine theta as well as fictitious force, because for non-inertial observer, the object is in equilibrium in the horizontal direction also. So fictitious force is equal to t sine theta. If you look at the equation, first equation, we have four equations on this slide. The first equation, t sine theta equal to ma, and fictitious force equal to t sine theta, we can conclude that fictitious force is equal to ma.